Hello, everyone, and thank you for attending today's webinar, Sensor Fusion, Steering Future Autonomous Mobile Robots, presented by onsemi. I'm Rebecca Kushmiter, and I'll be moderating this webinar. I'd like to start off by introducing our speaker. We will be joined by Theo Kirchis, System Application Engineering Manager at onsemi. You can read his full bio on the left side of your screen by selecting the Speakers tab. Just a few housekeeping notes before we begin. To access additional resources for today's presentation, you can click the Handouts tab button on the left side of your screen. You can access closed captions from the bottom right corner of the video player. This webinar is being recorded. It will be available to be watched on demand within 24 hours, and we'd love to hear from you during the presentation. You can submit any questions you have using the Questions and Answers tab on the left side of your screen. Time permitting, we will close with a Q&A session. All right, let's go ahead and begin. Theo, please go ahead.
Hello. Yeah, thank you for that wonderful introduction. I wanted to start with a slide here that shows some other presentations we did from onsemi about sensor solutions in the last month or 2 months. And this goes into depth for each of the individual sensors. My focus in this presentation is about what is required to drive safely these robotic solutions in industrial applications around and from a sensor perspective. I guess everybody has seen the agenda for today. I will do this for using pictures and images that you see, for instance, on the bottom of this screen, where you see kind of a play on the human evolution for robotics. And of course, at the right side, there's this looming, very impressive general AI-based humanoid that can do everything. And it's very interesting to see the progress we're making along the way, and also the challenges we're facing specifically for the sensor solutions that go into these products to drive these systems and realize computer vision and do the tasks they actually need to be performing. So what I'm not talking about is the big robots we had for many years since the 60s that move whole car parts around, that are in cages. Humans cannot go around them. What I'm also not talking about is this new development of the hive, or big computer system that controls many different individual mobile systems to do picking for grocery stores, for instance. You see here some of those applications. And this is because these systems don't work next to humans. They don't operate collaboratively with humans. Humans are not allowed in the space. I think another interesting criteria I think I'm going to use all out is that you can't buy one of them and then each year add one. You need to build this whole infrastructure first. You can expand it then, but you can do not a robot at a time. And so then the last thing is, why are even the lights on in these spaces? Because the robots don't need it. Definitely, because this is a central computer. It's air traffic system, they call it. It's all wireless, controlling these individual bots. So those are not the applications I want to go through. What I do want to go through, and you see a modified picture of this evolution, where there is a forklift truck here in the middle that kind of represents now the equipment that is automated for specific reasons. And in the case of forklift, it's either safety. There's 90% of forklifts in their life will have a serious accident. If you look at OSHA statistics, there's about 35,000 serious accidents with forklifts in the United States, where more than 90% involve the operator of the forklift truck. So you see a tendency for safety and also a tendency where labor shortages are, or labor is a concern. There's about 300% turnover in warehouses. And specifically, people that operate these sites say that 40% of them say that operators for forklift trucks are a scarce resource. But again, on the right side, there's this looming humanoid there. And so when we would eventually create this wonderful humanoid, do I really need any other smart equipment around it? Because you see companies today already have humanoids drive the car humanoids drive the not smart forklift, and then also have humanoids do other things. So there's this two-way where we have dedicated equipment, dedicated machinery that we're going to make autonomously. And then we have this activity to create this general smart humanoid that can take on many of these tasks. That would lead to probably more standardization, because the location where you can place the sensors would be very similar in all these systems. They would uh, all go to a specific place. And so there could be definitely good gains on safety and standards be made by going this route. Of course, there's a lot of social implications as well, and it's in one level also labor replacement. But there's also many examples, like the dog you see here. Things people come up with that you go, do I really want my furry companion be walked around by a humanoid? That relationship, he might love the humanoid more than he does you in the end. So that's kind of weird solutions. There is, of course, the self-driving taxi and haircutting and things that are being automated. There you might get a differentiation that people want to be serviced by a person and pay something more for that versus the automated solutions. And then, of course, you see AG tech or agricultural technologies, where you see a great benefit if you would have this humanoid that you can pick the whole year around. You don't have to have one day or several occasions during the year that you pick everything. You can just have them go every morning or every night in the dark, roam the fields and pick the right fruits or the right size eventually, and have huge gains from that. So that's the kind of the three way of things that are happening there. If you look at the industry, industrial revolutions, we're all familiar with the steam machine and the water pumps that, the 1760s or something, in the first industrial revolution. Every 100 years, we kind of go to something else, mass electrification. 100 years later, the computer and robotics. And then we start on a 30-year and a 20-year cycle. So it's actually accelerating where we perceive these industrial revolutions. And so we're in 4.0 at the moment. 5.0 is starting, but 4.0 is AI and empowered everything connected, big data. A really great example for that is, for instance, you have cameras in automotive, where a camera systems, where they collect this data and can have every road in a certain town monitored for potholes, and then get a report where the potholes need to be fixed, just as a side effect from having cameras in cars that you record the street with. 5.0 is building on 4.0 as an extension, and they now really focus on resilient, and comes out of also the pandemic we had, that people look at how we can make our deliverables sustainable and also resilient to impacts from outside. And also then the human-centric aspect comes in, where it's more important how to work together with these systems in this space. So that's kind of where we're heading. We go back though, little reality check, what is happening today. So many of these different robotic applications are being created that help us in various different scenarios. You see here many listed. And what all of these have in common is they have to have some way to drive around people safely and then perform a task. So the thing I'm mostly focused on is driving this safely, this platform that drives around safely. Whatever the task is a second order. There might be add more sensors, or just like in the top left, a rack to put boxes on. It can be all over the place, and so these things are not standardized. Of many of them, everybody is making their own solutions. and it's converging though with algorithms and the software side of things, with robot operating systems, etc. That uh, these things get some functions that are inherent required for each of these platforms to move safely around the environment. So we saw our customers make many of these sensor systems as well as robotic solutions. And we decided it should be fun to have, as we deliver many of these solutions, to create our own robotic platform. And that's this autonomous mobile robot you see here that we use as a demonstrator at trade show, and also as a solution integration for different sensors and battery operated power solutions as well. In this webinar, I'm going to focus on the image sensors and LiDAR, as well as ultrasonic, inductive positioning, and Bluetooth solutions. So the sensors more, there's other presentations we have that focus more on the power side of things, and other lighting, etc. So we started. For many years, we deliver sensors to the traditional industrial robotics after the robots got out of their cages and were used more on the industrial in settings, and have either sensors on them to be at least safe around people. So if people approach, they can slow down or stop, or have sensors on in the environment that detect people and can slow them down. So it's something that then progressed to the term where you see in the bottom the 6-axis robot, where we called it the cobot, collaborative robot. So now it could work next to a person and be safe doing a task together with that person. And these systems are very interesting and very popular, because you can get one of those arms and don't need to change much in your environment and have it operate a CNC machine. And deliberately, you want it not wireless connected to the CNC machine and operate it. You want a 3D printed knob on its end effector, for instance, to push the start and stop buttons like a person, so that if it's removed from the CNC machine, you know it's safe. You don't have to do log out, tag out procedures, but these machines work in environments where humans work as well, and you can then be safe doing that by following the same things you did in the past. If the robot is not close to this machine it operates, the machine that it operates is safe and to approach by other people. This now goes from collaborative solutions to what we call this adaptive solutions. And there's our friend again that looms on the right side. So this move from collaborative robotics to next adaptive robotics characterizes itself to do tasks or intrinsic safety and performance without compromise. You see, of course, a lot of medical solutions coming, elderly care, very fine motoristic things that these robots can do with their end effectors, and also very generic things like housekeeping chores or operating other machines in general. One of the things that held robotics a little bit back was, how do you instruct these robots what to do? There were, of course, inroads made with these robotic arms again to use waypoints, so you can move the robot and program it that way, so you don't have to actually program something. But now with the advancements of course, the large language models, you can instruct it what to do and have it have a really good interaction with these systems to have them do what you want at certain times. And they are also more capable then to perform tasks that traditional robots were not able to do. You saw every week there's a movie with robots dancing and jumping and doing things we couldn't believe they could do before. So that's very interesting and encouraging. And then the increasing demand for automation due to this for difficult tasks or labor shortage is something that this is a continuing path for that we're on with all this automation. So here I'm showing some things that go wrong with in the past, and these are some of these systems are learning systems, so they have to learn from their environments they're in. You either can do that in a simulator or in the real world, but they have to be deployed at some point. But there are some challenges that also can be unsafe. It's hard to find any pictures, particularly for industrial applications, because there are more private property areas. But in the public domain, you see many of these solutions failing, and they're interesting to look at. When I saw some of these, I tried not to capture the final picture of what happened, because that with that scenario was not, or what happened exactly was not so important, but more why it happened is important. So let's go to some of these. On the right top, I put 3 of these mirrors. These mirrors seem to be very exotic for some of the robotic perception systems. Because how does the robot know? It looks in the mirror that something is coming around the 90-degree bend from it, some angle, either in an industrial setting or in an automotive setting. Those are not even real road signs. So if you don't have another sensor modality like a LiDAR or something, you would not know in the top left that there's a wall, maybe if you only see the mirror image of this solution. Right to the next picture, to the right of that, you see a box truck. There seem to be box trucks falling over left and right. This one is laying on the side, so you see only the top. It's a white top, and the sky is very white as well. So in this endeavor, the person that drove the truck walked about 150 feet in front of it and started directing traffic, self a little dazed, but warning traffic and pushing traffic to other lanes. Of course, there was a self-driving car that just plunged into the truck. And the concept here, Joe, is, first of all, if you have image sensors, how do you recognize what this person is doing next to the road? Your mobile robot may just be happy it detected the object and didn't hit it, but actually it needs to see from the demeanor of this person that they're in distress and we're doing something there that is important for you later down the road. And secondly, then it didn't detect this the top of the truck as a barrier, and maybe with its image sensors, whereas it would have radar or LiDAR or another technology, it could have detected that. Similarly, it's hard to detect just poured concrete. People drive sometimes into it, and it's harder than you think, because you could say, well, who drives into this? But if the truck that pours it is coming and going, there is an open road, there might be a sign that says don't go in there, but it might not be blocked off. And so hard to detect what this exactly is, and for people very easy to detect. Same with this security robot that thought it could walk on water, and so it just went into the fountain. By the way, the captions of these events are, of course, hilarious sometimes. If nothing serious happens, with like um, security robot kills itself in the fountain and that kind of things, and that's why you probably don't see many of these things in industrial settings. We don't like to get that come out particularly. Other examples in the bottom here, a ball on the middle of the road. So your system in the first instance may be happy it didn't hit it and it's evaded it, but it needs to know that kids may go run behind it. And these are scenarios that are not often happen, so you have to use simulation environment. I'll skip over the middle one quickly and go to the right, where you see the most right picture, the first autonomous car hitting the first autonomous robot. So that happened already. And then in the middle, there's a picture where workers that go into the warehouse will have a harness with them, some electronic device that actually makes sends a signal to the mobile robots that they have extra safety that these stop so they can be worked on. So I mentioned already that water and concrete hard to detect. Also, edges are very hard to detect. Specifically, now if you look at a certain other a 2D lidar, you might look over the edge of something if that is below or above your field of view. We run into that ourselves with our mobile robot, which we use at trade shows. So in the top level picture, it's on a table and it drives around. But in that setting, the LiDAR would just go over the table and show the walls of the room, but it wouldn't see that edge of the table. So that scenario, we had to create something where we did electronic fencing. So you see the second picture where these orange cones would be detected by the LiDAR. And with that, we could change the algorithm of the navigation stack to make those walls between them. So to increase that that chance that the robot drives off something to very low chance. In the middle, you see a picture where security robots have the same issue. They may be on the second floor looking through a big railing there that is so open that it doesn't detect that railing, and there might be issues with that or other complications in certain scenarios. And even forklift trucks that are driven by people have their own category for injuries that are related to driving off cliffs and edges. So people also have issues with these scenarios. I haven't even talked about deliberate or weird scenarios. You see some here where vandalism seems to be funny to push delivery robots over. The second picture is interesting. It's the first attack by children on a security robot. And the cool thing about that one is the first announcement was robot tries to escape from children's attack. This was a little article. And then a week later, there was children beating up robot inspired a new escape maneuver system. So actually, the company that makes that robot integrated some new software that it can detect these scenarios and try to evade them. There's some other solutions, problems shown here. The bottom right ones are some of the nasty ones. These are very easily detected by people. If we see something from dogs from the front or the back, then we don't step in it and walk around in it. Apparently, robotic systems are more challenged with that, with liquids in general. So this applies for industrial settings as well. And they need to have a special training on that. And then the bottom left picture is where in our industrial setting today, we see humans next to automated systems as well as forklift trucks that are still driven by humans. And that seems to be causing problems because there is now a focus on human drivers hitting autonomous systems in these settings. And what they're doing is adding to these industrial forklift trucks sensors that can detect the autonomous systems and then stop the forklift truck. Of course, the autonomous systems have their own sensor solutions. They don't drive into the forklift trucks. It's always the forklift truck. And this is also one of the reasons people look at making these more safe by making fully automated forklift trucks. Which then introduces asynchronous or different types of mobile robots driving around from maybe different vendors that have different types of sensor solutions on them that need to be matched in some way. Lastly, here on the right, the picture shows a autonomous mobile robot of a forklift truck with some lighting to warn people that it's coming around the corner. Very common also on regular forklift trucks. But how do automated systems see that light and have to recognize that then as such as well? So many different things that can can happen with these systems. And the best practice is to control the environment, and that's really good because in an industrial setting we can do that. We don't have kids that play with balls in warehouse or with toys. We don't have a lot of vandalism or deliberate undermining the robotic systems. There's more control in these settings. And also, if the robot sees something weird, it can actually stop. This is a big issue because with autonomous cars, of course, if you drive on the freeway, on the highway, and it sees something weird, it can't stop because then it would be a hazard. And in our environment, it can do that. So we have a good way of using that we can control the environment by letting the systems learn then in that space and also be safe still around it. Secondly, the best thing to do is always simulate your environment. If that security robot with the fountain would have driven around on the same route in a simulation environment, it would, they would have seen that it would drive on water and it wouldn't drop into the water. So digital twin simulation environment, very important. I got many years ago, I saw this simulation with this four-legged robot walking around, and they spawned 2,000 of these and had them run overnight in the morning, downloaded the code on this thing, and it could step up and walk and follow and walk stairs and do things. So accelerated learning with AI, the equivalent now they do with the humanoids that all are announced at the moment. Same scenario. They even have some gravel here or other things. These simulation environments become more and more realistic and accurate. Here we see the ball with the person we talked about earlier, and the kid is now coming into the frame. So you can teach your systems on the synthetic data or data that doesn't exist in the real world, or you create in your virtual space to train your system to behave in those kind of scenarios. The good thing, or what would be nice, is if you have a standardized certification for something. So you'd say, hey, if you run 1,000 hours in this simulation with whatever 2,000 robots spawn, you get a certain certify your product to be safe in this class of industrial setting, or last mile delivery, which is another can of worms, where there's sprinkler systems, there's kids deliberately again could do stuff, etc. So you have to simulate these scenarios. So the takeaways for these observations is control your environment, limit what the robot can encounter, um, define the safety stops and slow down if that's possible. So make procedures if the robot still has an issue that it can safely park or do something. And then sensors, we can add sensors in the environment for if you control the environment, the sensors you use to safely drive around don't need to be all on the robot. They can also be in the building or on other robots, and they can share that information. Simulate your environments. Digital twin would be nice to have standard certified simulation environments, but if not, then you're the expert of your environment. If you're in agricultural or in medical space, and you would think of these scenarios and create them in wonderful tools like the NVIDIA Omniverse. And then lastly, you need sensor fusion and sensors in general with really good algorithms that also are redundant and give you the safety for these kind of solutions. So this is just a slide I got from one of a sensor solution creator. You see he has some kind of product where there's a PCB. Our onsemi sensors would be on this PCB, and the integrator would make this whole solution. They add a lot of tests around this, like environmental testing you see here on the left for chemical and resistance, shock and vibration, humidity, and all these things. And when you use these sensors in your robot, you better get the right category. You see here 3 of these categories, and so that's something to be aware of. So then sensor fusion, what is it? Basically, it's two or more sensors combined, and or an algorithm and a sensor as a minimum combined. into something that fuses the information from these sensors, that then gives you better reliability, redundancy, safety, more consistent measurement or accurate measurement, or it's more dependable. So there's quite many different things you can get out of it. We show here our mobile robot with its sensors. This is a sensor demonstration platform, so we're not really putting anything on this to drive around with it. But if you would, you need the sensor as a complement there on the other axis as well, to have a 270 degrees view on each side, because you cannot look through what you're driving around. So some examples of this sensor fusion from everybody can relate to. The start here is surround view, or a surround boat view, and it combines your image sensors, stitch those images together. The consumer of this information is of course a human in this case. It has a rotational angle for the wheels, so you can see these green lines where you end up, and it has an ultrasonic sensor to measure distance to objects. And so these three informations are merged, and you can make applications for that. The second example here is a security system where a single camera with depth sensing can look at a face and determine that it's not a picture, it's not a flat object, but it has depth in it, and it can do facial recognition as well. So it's a more secure platform to use that. With ADAS solutions here in the black and white one, we can even look at if people have their eyes open or their pupils are moving, and so have different states, and add that to the security of a system or to an alert system. You see also that this picture is black and white. These pictures tend to be consumed by computers if we're using black and white imagery, because we don't need always color images for computer consumption of the sensor fusion. And then in the bottom here you see our mobile robot, again driving around with its camera in space, and it saw a Ruko marker and determined the distance to that marker, and puts all kind of signals around it, so you can visualize the sensors that you have on your robot with tools like Foxglove or Arvis, and etc. So many sensors we integrated. The sensors are listed here into our robotic solution, and then there are also models and algorithms. Models can be very simple. For instance, a robot cannot drive on the ceiling. It can be a model, so you don't take that into account, or cannot be upside down or anything. An algorithm, of course, is very complex, can be very complex, and there's where most of the new things happen currently, where a lot of algorithms are created very fast, and it's very interesting. And then we can still have this angle from other sensors, that wirelessly we get information from other drivers or other units around us. So the whole path to drive autonomously, you have a physical work, you collect your sensor data, you have to perceive this world, this data, then you can plan an action and follow the action. The part that is sensor fusion is where you collect the data and perceive this data with algorithms and processes. So some of the things you can do with that is reduce noise, so making the data more reliable. If you have uncorrelated noise in your system, you can have multiple similar sensors, so homogeneous sensor types. So 2 accelerators gives you a 4th more accuracy. If you have correlated noise, you can use different types of sensors. So you can do a LiDAR and a stereo camera, or a magnetometer and a gyro. So this increases also your redundancy. If one system falls away, you can still leap out of the way or do something before you really have no data anymore. And then the last one, with sensor fusion, you can estimate unmeasured data. The big example there is, of course, stereo cameras. None of the individual cameras have depth information, or they do have the depth information in them hidden, but you need 2 of them get angle or, measurements, and then do a depth calculation for those systems. As mentioned, trends in sensor fusion, it's really AI. Everybody's on the AI algorithm creation. There's a lot of research done and happening. NVIDIA just launched a Deep Stream 7.0 last month, and they have really interesting algorithms where with single cameras you can, even from a head and a partially torso, determine where the feet are of a person in areas. So these are very interesting developments, and so this enhances object detection and classification. There's a lot being done, what I mentioned now a couple of times, where sensors are cooperated. So you have, for instance, the front robot here driving, and its sensor data is sent to the back one as well to use. So it can see ahead of its other places, or in buildings, or in settings where something happens in a space. The robot doesn't have to see this itself. It can get this warning from other wireless method, and then change the path already. Another very important thing is environmental perception and advisory conditions. So if you have bad weather, sunlight, and those kind of things, then that's also an area that is under a lot of things happening. And then real-time sensor calibration and robustness of your calibration processes for sensors. That's something that is actively worked on. So if we look at specifically depth sensing, onsemi has several different technologies. Of course, stereoscopic. We're a leader on image sensors. There could be two cameras or more. We do time of flight, a direct time of flight with LiDAR, and we're now coming out with some products for indirect time of flight, as well as ultrasonic solutions we have as well. So here's a graph that with data I got from some people that make sensors and use them in robotics end products, and what they thought is important for these sensors. So you see things on 7 o'clock here, night and direct sunlight perception. We see, by the way, this green bulb is a human being. So they're not so good at in the night and direct sunlight. They're very good at color detection, at object classification and object detection. We mentioned that already. They will see if there's something on the ground you don't want to step in, recognize that immediately, and etc. So speed. This graph is kind of weird. Some things are more is better, and some is more. Cost more cost is not good, obviously, but the whole purpose of it is just to get an indication and comparison between different sensors, or identify an area where you could improve a certain sensor. So I'm just overlaying here different sensors, and I'm not going to talk too much about them due to time constraints, but this last one, which is the worst color I now see, is a stereoscopic camera, and you can see that the perception by customers was that they were not so good at night and direct sunlight. So this was some information we saw some time ago, and we thought, oh, we have to do something about it. So can we improve this night vision and direct sunlight, as well as can we improve range or speed of camera solution, which were other areas where the perception was there's a little thing we can correct and make this better. So this perception of dynamic range, or in the physical world where you have sunlight directly behind this traffic light, or sunlight in your warehouse coming in, or in agricultural settings, then there's a lot of dynamic range in the picture, and image sensors could really benefit from a boost in some technology to solve these solutions, and we created several sensors to do that. And what these sensors can do is what you see here on the side. When you look out of the tunnel, the bottom one doesn't have our HDR technology, and basically there's a wash out looking out. The top one does, and you can actually look outside the tunnel and detect what's going on there. So with these systems, or with these solutions, it's really, you can make the fanciest algorithm you want. If you don't have any data in here, you can't do anything with it. So the sensor quality and sensor features are very important for creating good solutions for self-driving systems. Second thing, which may be important, is something that's called rolling shutter versus global shutter, where if you have very fast objects, rolling shutter can distort the image because you're capturing each line by itself. This may or not may be a problem, because if you put a bounding box on the train and you take the furthest point, you still get a safe area that might not be an issue at all, and you have a good sensor. But if you have you look at some very fast motion on a fan blade or something, then you might want to look at that in a correct way, and so add a camera sensor that can handle that properly if you need that in that scenario. Or you might have both of these sensors on your system to handle different use cases. So for image sensors, we have this whole collateral of from technology to fab to device die, then modules and software. And one of the things I want to highlight in the bottom here is this Prism. So this premier reference image sensor modules that we are creating, and these are seen here in the image. They're very small, but we have adapter boards to the main computer systems that are out there, like the Jetson Nano and Orin and other systems, NXP and Qualcomm, to get you going very fast with our image sensors in these solutions that are used for these robotic applications. Jumping to another light system is a LiDAR. We talked already about it. I'm going a little faster because I'm running out of time. But obviously there is the single shot LiDAR, the 2D LiDAR, where you get a horizontal 360 if it turns around view of what's around you. But as mentioned, anything below the field of view or above the field of view of that 2D LiDAR, you might not see a cliff or an edge or a rope or anything like that. And so you can have multiple 2D LiDARs to solve that issue. Or you can also have 3D LiDARs that give you a more complete image for your surroundings, and deal with it that way. I already went over this. This basically lists what you're missing sometimes with 2D LiDARs that we see in the field. So empty pellets, cliff detection, rope and barriers. There is some future reading here, links in the bottom about these problems and how to address them. I'm skipping over these slides, which go into more detail over how LiDAR works. There's, as I mentioned, a very detailed presentation on that. Here you can see the light, the frequencies or light wavelength we're using for some of our technology, and why that is. So we use silicon detectors because they're very cost optimized, and you have a lot of laser diodes for those systems. If you go down or your wavelength comes into the color spectrum, then for outdoors applications you have to also more noise in the system because the sunlight is there as well. So there's decisions and compromises on what wavelength to use for your specific solution. Of course, these work in dark environments. So if you're in an industrial application where the warehouse is dark in the night, because you're carrying your own laser light with you. There's two examples here of products we currently have in the market with our silicon photon multiplexer, and then I have here an example of that device that's available. There's a development kit that people can use to create a solution for that. Next, so we talked about light. For location or depth sensing, if you want to do location, you actually can define what it means to be able to determine your location. Um, you can also do that with RF, and you can do it with sound. So we talked about light. If you do this uh, with RF, we have a Bluetooth Low Energy solution subsystem and a complete product with the UniKey that can use angle of arrival and angle of departure for your indoor positioning system or a location service. And the difference between the two is which one, if the transmitter is moving or the receiver is moving. So that's how you can uh, distinguish these systems and dive more into these solutions. There's a link for that as well. And then lastly, ultrasonic solutions, so sound solutions. We have a sensor kit for that, and this comes from our automotive side, but we also have this for our robotic solutions. So using ultrasonic sound for different applications, that's also an option. So then, lastly, we can talk about positioning, and we have a inductive positioning sensor, a rotary sensor, very accurate, um, 50 arc seconds, and there's a second version of it here as well, and you can see maximum rotational speed, etc. Definitely something we have in our solution to detect position of a robotic the 6 degrees of freedom robotic arms, or even a robotic wheel, where you can detect if your wheel is spinning or other things happening with these sensors. With that, it's my last slide. I think if on the path we're up and getting better sensors and merging these with better algorithms, we definitely get a situation where we can have these robotics go out of their controlled environments into more generic environments and be safe around humans and assist us in different tasks. I end with the same slide I started with. Different presentations that go in depth of each of the individual sensor solutions and the names of some of the contacts for these solutions, or these people that give this presentation. With that, I give it back to the host.
All right, well, thank you very much. And we can move on to the Q&A now. I see we've got a lot of great questions already. We will get to as many of them as we can. Let's go ahead and begin. What are the challenges faced in synchronizing data from multiple sensors in real time? For example, if there are conflicting information.
Yes, so you can imagine if you have a stereo camera and you have two images from the individual cameras, these have to be synchronized, um, because if you would have fast movement of the system with the two cameras or a fast moving object along there and the camera images are not synchronized, then your algorithm that calculates the depth from these images it's not correct. We'll have errors in it which are bigger than you would if you. So in that case, it's very important to synchronize this data. Um, if you have conflicting data, which is the question specific about conflicting data, it's also you have to have a predefined path to what you're going to do in these scenarios, and one of them is to, as I mentioned already, a very beautiful one, which is slow down or stop, which we have the option to do in many agricultural and industrial applications, and you can do in automotive applications. So those are how people handle these scenarios.
Great. Well, thank you. For the next question, what role does machine learning play in the development of advanced sensor fusion techniques?
Yeah, a very big role. And I think I showed the simulation environments that become very detailed, and you can collect and take objects from imaging and images and use them in your simulation environment to create and then train neural networks to walk and be safe around humans, and do other use cases that are not normally. We want to test them. We don't want to have them learn in real scenarios, like the example with kids playing, or other scenarios where there's animals around that do things that don't happen often. But if they happen, humans tend to have a common sense or some kind of a easy handling on these scenarios, and we have to really define these in the simulation environment to run them and make sure that the machine handles them in the same way.
All right, thank you. What are the future trends and research directions in sensor fusion?
Yeah, I mentioned some already. I had a special slide on them, so I think that's answered by going through these. The one thing I might want to highlight from the slide, as it's not the most exotic, or everybody wants to go the AI route again and algorithms, but how sensors are calibrated, and how sensor systems as a unit work together and are calibrated and maintain their relevance during the operation of the system, are very important for these systems.
Okay. What are the key technologies for robot-human interaction?
Key technologies, so examples of what we're using them for, or I'm not exactly sure what's asked there, or how we do this safely. Is that we've started maybe the safety aspect first. We started, of course, with robots that you can bump. They have a sensor in them, acceleration sensor or something, that if you bump it with a certain force, it would stop. They tend to be safe, except if they would have a scalpel or some knife in their sharp thing, they would still pierce you, or do some damage. So their image sensors are used, camera systems are used to create these safety bubbles around these systems, and that also applies then to the mobile system, where you want maybe a 360 safety bubble around it, that humans approach, it slows down and stops fully, or deals with the situation as needed, as appropriate for that use case.
Okay. For the next question, are the sensors used on autonomous mobile robot slide all made by Onsemi, for example, LiDAR, ultrasonic, etc.?
Yeah, so yes, the integrated circuits are made by onsemi, and our partners make the sensor solutions. So a full LiDAR system that a robot company would buy to use on their system would include our products. So our customers are directly sensor integrators, or make integrators, or people that make sensor solutions like camera systems and LiDAR systems and ultrasonic systems. But also sometimes, if there's special requirements, we talk to people that have their end application, and we bring all the parties together to get the right solution for that.
Great. Moving on, how do you address adverse environmental conditions?
I guess we talk about fog or night rain. So there you have, with rain, for instance, you can have different sensor modalities that are more affected by it than others, and then use those. An easy example is against stereo cameras, with where you use environmental light to look into something. If it's dark, you don't see a lot, but then you can use a LiDAR or an ultrasonic system or an RF system to augment and get the data and location information you need. Um, we talked about the high dynamic range for our sensors. So that's definitely a use case where we increased our technology to be able to use this very bright sunlight behind another object to still see the street light or still see um, the environment in that space. So there's another example.
Okay, one more question here. How is sensor fusion actually brought about? How is it materialized in the robotic system device?
Yeah. So there is your product. I had one slide where it shows the steps you take in, for instance, we use a lot of the NVIDIA's environment and systems. So in DeepStream, you have several steps how you integrate the different modalities of your sensors, and then you get into the navigation stack of that solution, and go through the different steps of this with, for instance, a robot operating system, ROS. We use ROS2 in our example, and we utilize these programs and solutions. But a better reference there would be to look at NVIDIA, for instance, on their website with their learning solutions for the algorithms, where they do segmentation and those kind of things. So it's more on the compute side after you get the sensor data in. But again, I hope I showed that you need good sensor data, because if you don't have that, then the algorithm can do nothing.
All right. Well, we are coming to the end of our time here, so we have time for one more question. Sorry to anyone we didn't get to your questions. We will try and get back to each of you individually later. So to wrap up, can you use BLE mounted on an AMR?
Say that again. What was the first part?
Can you use
DLE?
BLE mounted on an AMR?
Yes, of course. We have even seen it in. It comes from a different use case. So we had a battery-operated sensor node that would even take has some other, in addition to the RF solution, to look at location. We had it as a environmental sensor connected to it. So you could mount it on. They're very small. They're these tags that are made by other companies as well. You can have them on your helmet, for instance, and have if there's a gas leak or something, it can immediately detect that and also give warnings on that and see where people are. For in the situation if there's fire in the building, it can immediately pinpoint where everybody is. So you can directly use a solution like that on your AMR and just stick it on there. And this also comes into the realm of Edge AI, where we had it mounted to systems that were not at all smart, maybe like a cutting machine, and it would be able to sense or from sound or from vibration if the knife gets dull in those scenarios. So yeah, definitely you can place these on any equipment to locate it and or to use it for tracking.
Well, thank you very much. And thank all of you for attending today's webinar. Thank you for submitting so many great questions. We'd also like to thank our speakers for participating. A recorded version of this webinar will be available for you to access within 24 hours using the same audience link that was sent to you earlier. Thank you again for joining, and we look forward to seeing you at future events.